Okay, good morning. I just did a video about grade boundaries changes. Um, this is the first series of exams for units 1, 2 and 3 which were available for the new specification for the International A-Level Edexcel Physics. This is unit 2. Some of my students are retaking in October to improve their grades depending on which university they're going to. So a student of mine asked me to have a look at this paper, and I just explained how the grade boundaries had changed from 2019. So this was pre-COVID. In 2020 they cancelled the exam. And here's a comparison of the video for the video I just made. You'll notice in 2019 to get an A you need 42 out of 80 for unit 1. For unit 2 was 50. Then in COVID years, the last COVID period was June 2020, the 43 for Unit 1, 49 for Unit 2, and you can see a comparison with the C grade and the E grade as a comparison. Then suddenly in June 23, they went back up to 53 and 55, so they became 10 marks more difficult raw scores to get an A, and then in 2024 they've gone up another 8 marks, so the grade boundaries are going higher, it seems, for Unit 1 and Unit 2. If you look at the same ones, Unit 4, they didn't have a 2019 exam. Their first exam was in January 2020, which is before COVID as well. And Unit 4 is out of 90. So they in that one, pre-COVID, 56 out of 90 would get you an A. During COVID, so up to 2022, and I use the 2022 exam as a comparison, it went down to 48, so it was easier during COVID years to get the grade A. And you can see also the difference between C's, 12 marks lower, 15 marks lower for an E, so during COVID years it was easier. And then in June 23 it went suddenly from 48 to 73, which is a huge increase. Likewise 34 to 58, 22 to 44, so double. You'd have to really do better. So the people who had to take their exam in June 23 were disadvantaged compared to the international students doing it in January. And likewise in 24 they've brought it down a bit. I did say, to having looked at this, that I think that the Unit 4 one was too high, and they refused to change it between June 23 for October and January 24. They didn't change it, but they've now brought it down 4 marks, which is reasonable that at least it's been decreased, and there's 3 marks and 2 marks, so it's at least now heading in the right direction. So I thought that was useful for students to see. So you can't be sure unless you're looking at an up-to-date grade boundary. So this is Unit 2 to revise. So the first question on this is multiple choice, and it wants you to just know a definition. Definition of EMF is a voltage, which is energy per unit charge, so you just need to know that EMF is a voltage. Looks like the autofocus is still not working as well as it should, and I got the vacuum cleaner going on in the other room behind closed doors. So hopefully we'll just do the multiple choice and see if it's good enough. The next question, so on the right hand side I've written notes for you. So the technique I want you to use is to see, okay, it's an SI unit, it's EMF, you need to know, they just want you to know what EMF is. Second one, a lamp is a source of unpolarized light. That means the vibration is in multiple planes and directions. It says the polarizing filter is placed between the lamp and an observer. The filter is rotated in the perpendicular plane to the direction of wave travel of light. So the light's just coming through like this. Polaroid filter, like you'd put it in a way. And then it says which of the following is observed as the filter is rotated through 90 degrees. So if you imagine it's 3D, if you rotate it through 90 degrees, it will just change the plane of the polarization. So only one filter they're talking about. So light will always be polarized now. So before it was unpolarized, but rotating it through 90 degrees will not change the intensity, because here they're asking about intensity. So you need two filters to change the intensity, and they need to be at right angles. They're plane of the Polaroid crystals, which is basically what a Polaroid filter is. So the light intensity does not change, is the answer. If you read through the other ones, you will understand what I mean. So the light intensity only changes if you've got two Polaroid filters at right angles to each other. Okay. Question 3 says, when a guitar string is plucked, a sound of constant frequency is heard. Yeah, that means it's a stationary wave, because it's on the guitar string. They want you to say the wave produced on the vibrating string. They're not talking about sound waves. Sound waves are longitudinal, but stationary waves on the string are transverse. So we're looking for transverse, which is C or D, and they're stationary, so it's B or D, so it must be D. Okay, the endpoints are fixed points, and between you have an antinode, the simplest form, the fundamental frequency. So that's question 1, 2, and 3. Sorry about it being slightly out of focus. I think I have to restart the computer, and when I get through the multiple choice. So you just have to do the audio and make sure you've got a copy in front of you. Which of the following has the largest de Broglie wavelength? De Broglie means, this is how you pronounce it, French name, yeah. So lambda wavelength is h Planck's constant over p momentum, so h over mv. Lambda therefore is proportional to 1 over m, and so inversely proportional to mass, and inversely proportional to the velocity. And here they're given you neutrons and electrons, so obviously the one with a lower mass will tend to have the larger de Broglie wavelength, okay, because lambda, if m is small, lambda will be large, inverse proportion. And likewise, you want to have, for a larger wavelength, the electron with 3 times 10 to the 5, the smaller velocity will also increase the de Broglie wavelength. So the answer is A. Okay? So for large lambda, we need a small mass, ideally, and a small velocity. Okay? So it's just inverse proportions that they want you to do. So a lot of these questions are just problem solving. You just need to make sure that you know enough about the topic to be able to do it. Which of the following graphs show how current I varies with potential difference V for a negative temperature coefficient thermistor? Negative temperature coefficient thermistor means as the temperature increases, the resistance decreases. So as voltage increases, and obviously current will increase too, the temperature will increase just from the extra energy, because voltage is joules per coulomb. So you're giving the charges more energy, so they will increase in temperature through collisions or whatever mechanism it occurs. So that's why the voltage goes up, the resistance will go down. And the gradient of an IV graph is it's the inverse of resistance. So the gradient of an IV graph for lower resistance should be steeper. Okay, so if it was a V as opposed to a VI graph. So a VI graph is V over I, the resistance is proportional to the gradient. But since it's an IV graph, the 1 over the resistance is proportional to the gradient. Okay, so this is a fixed resistance, so this is not changing, so it can't be A. This is an increased resistance with voltage, but we want a decreasing resistance. This is the only one where it's decreasing. This one is increasing as well. You can see the resistance is increasing and eventually becomes infinite. So the answer must be B. Okay? So let's have a look at the next question. Just filling the mark scheme out to make sure we're on the right page. So we're on question 5. So the answer should be C, decreasing. Did I say B? We want the decreasing resistance, yeah? So we want R to go down as voltage goes up. That's only C. I think I misspoke when I was talking. Okay? So that's question 5 over the page. Question 6, yeah. What's happening? Question 6, a string is stretched between two fixed points and set into oscillation. So again, we're talking about stationary waves. The equation they give you is V equals the square root of tension over the mass per unit length of the string. But you also know V equals F lambda. And the question is about frequency. So you need to change velocity to F lambda. The frequency of the vibrating string is not dependent on which of these. The answer is A. It's not dependent on the amplitude of the strings. Why? The length of the string, lambda, for the fundamental frequency, remember if the two ends of the string are fixed, the fundamental frequency will look like that with two nodes and an antinode in the middle. So the lambda for this fundamental frequency, you can see that's half of a complete wave, full wave would go down as well, is 2 times the length. So the length is affected because it's in the equation. So you can change lambda into 2L, and you can put frequency on the left hand side, so it'll be 1 over 2L. So you can change the algebra of the equation using these two equations together, and then inserting 2L for lambda. So B, the length of the string does affect the frequency. The mass per unit length of the string is mu, so that's in the formula. So the mass per unit length of the string does affect the frequency as well, as does the tension, so the only answer can be A. Okay, the next question about ultrasound wave going through a material, the solid object. The transducer is the energy, part of the diagram where is producing the ultrasound. So the ultrasound transducer comes down here, goes down 10 centimeters, comes back. So it's emitted, and then signal is received when it goes back and up, there and back, an echo. A pulse of ultrasound is transmitted into the object. The pulse is received at the transducer 50 microseconds. So remember, that's 10 to the minus 6 microseconds after it is emitted. Yeah. So it echoes off the bottom of the block, comes back. Which of the following can be used to calculate the speed of sound? Well, speed is velocity is distance over time. The distance is 10 centimeters to go down, so you could change this to 25 microseconds because time to go down will be 25 microseconds and time to go back up is 25 microseconds. So you put 10, I forgot to put it into meters, so don't forget to put the 10 centimeters into meters, divided by 25 times 10 to the minus 6, half of the time to go down, half the time to return, and you will get the answer 0.10 divided by 25 times 10 to the minus 6 seconds, that's being microseconds. Yeah, so remember micro is 10 to the minus 6. And that's how you do question 7. Question 8. Question 8 is about two copper wires. Two copper wires, so they have the same number of free electrons per meter cubed of identical cross-sectional area placed in series in a circuit. If they're in series, the I must be constant. So the two copper wires tells you that you're talking about N for copper. Which of the following could be different? Well, you have to remember the equation is I equals NAQV. This is on your formula sheet that they give you at the back of the exam. Which of the following could be different for the two wires? N is the same for both wires. Current is the same for both wires because it's in series. The drift velocity, if N is the same, A is the same, they tell us. Q is electron for both. I is the same, that means V must also be the same. So it can't be V, but there can be potential difference. Potential difference can vary with the length of the wires. They haven't told us anything about the length of the wires, so it could vary with the length, and therefore the potential difference theoretically can be different. I hope that is clear. Question 9. The definitions for current and potential difference both include something the same. I is Q over T. Yeah. Current is charge over time. Voltage is energy per unit charge. Both current and voltage are defined in terms of charge. Okay, one gives it flow. One is a measure of the flow of the charge, the rate of flow, and voltage is a measure of energy per unit charge. Finally, question 10, yet another stationary wave. So you need to make sure you understand them. The two diagrams show how the displacement varies with distance along a stationary wave at two instants of time. Two instants of time is when it's at the top, and when it's at the bottom, the dotted line, so obviously it's vibrating up and down at the frequency of the oscillation. So it's a displacement distance graph. So these are the nodes are at the end. There's also a node in the middle. So this is the first overtone, not the fundamental frequency. So here the length is equal to the wavelength. Which of the following statements is not correct? So always make sure they put it in bold to make sure you're not misreading it. Points X and Z are in antiphase. X and Z are in antiphase. It's correct, they are. Points Y and Z have the same amplitude. Well, you can see they haven't got the same amplitude because amplitude is the distance from the 0 point, the non-displaced position. So the string, when it's flat, will be there. Okay, so we know it must be B. Just go through it. Points Y and Z have the same frequency of vibration. That's correct because they're moving up and down together. It's just Y doesn't move down as far as Z because Z's in the middle at the antinode center. And point Z is an antinode. That is correct. So the only one which is incorrect is B. So that ends the multiple choice section of the paper. I apologize for the lack of autofocus on this Chinese bought device. So I have spoken to them. They are able to get me another one, but I think it will be difficult to do. Sometimes when I restart the computer and start it again, it works. So I'll do that for the next section. So give me a like and share it with your friends, and shortly I will be doing the short answers in a separate video. Okay, so subscribe if you want to know when the next video is ready. Thanks for watching. See you soon. Bye.